Hello students, I am Dr.PHYSICS. So welcome back to my YouTube channel Dr.PHYSICS by DYSP. So now in this particular video I am going to discuss the concept on flywheel. Okay, so I think it is a very basic concept to understand the wheel mechanics. Okay, now let us see what is flywheel and how to find its moment of inertia. Okay, then what is flywheel? So the flywheel is a very simple device. Okay, so it looks like this. So just look at the diagram. The flywheel consisting of some heavy metallic wheel like this. Okay, at the center you can see that it is fixed to a metallic axle. Okay, a long metallic axle will be there like this at the center. So that we can expect that whenever the axle is made to rotate, the entire wheel is also rotating. But how to rotate the axle? Just it is very simple by fixing a thread. Okay, thread to the peg P, and it is wound some number of turns, and other end of the thread is fixed to some mass. Okay, so that the total weight of the mass will be equal to m into g. Okay, now based on the weight, okay, when it is starts pulling down, the axle made to rotate. How many rotations of the wheel is made? That depends upon number of turns on the thread. Okay, if n number of turns are there on thread, then wheel is expected to rotate n number of turns here. So like that the flywheel works here. Clear? So what is flywheel? Very simple concept. So it is a large heavy wheel, we can say, with a long cylindrical axle passing through its center. The center of gravity lies on its axis of rotation. The whole center of gravity always lies at the on its axis of rotation. Means that axis of rotation will be like this. So this axis of rotation. So when the wheel is rotated about the axis of rotation, it looks like this, right? So when it is mounted over the ball bearings, we have to mount the entire instrument on some ball bearings so that the friction will be less. It has to rotate with the less friction. Okay, then only it comes to rest at any desired position, right? Wheel support, ball bearing support should be there with less friction. Then it is made to rotate, and it can come to rest also at any desired position. Such a simple device is called now flywheel. Okay, now how to find the moment of inertia of the flywheel when it is rotating about its axis, about the axis passing through the axle at the center of the wheel also, right? So for that we should know the mass of the wheel, mass of the axle, the radius, etc. Okay, now look at here. So to find the moment of inertia, let us consider capital M as mass of the disc. You can call it as the disc or wheel, right? Both are same. And correspondingly small m we can consider separately. Small m is mass of the axle which is passing through the center of the disc. Okay, and capital R you take radius of the wheel, and small r as the radius of the axle. Okay, these radius are measured from the axis of rotation for the axle and for the wheel, right? Okay, now the wheel can be considered as an annular ring also. The entire wheel can be considered as consisting of number of small annular rings, and the whole annular rings will make put together will give you such a big metallic wheel like this. Okay, so if it is considered as annular ring like this, the outer radius of the annular ring is considered as r, and because there is a hole, small hole, radius of that small hole from this axis of center is equal to radius of the axle also, right? So we can write now the wheel can be considered as annular ring, outer radius r and inner radius is small r. Then you know that the standard equation for the moment of inertia of the annular ring, the moment of inertia of the annular ring or disc is given by, so I1 is equal to m into r square plus small r square, outer radius r square plus inner radius small r, so that is r square divided by 2. So that is standard equation of mr square by 2 as the moment of inertia of any annular ring. Now it is consisting of two radiuses here, outer radius, inner radius. You have to consider r square plus r square as the total radius, and hence mr square plus r square by 2. Okay, now the axle also can be considered as a disc. Now you can just consider separately what is that axle. Axle also looks like a disc, okay, with so much of length, that's it, but moment of inertia formula will be same. So if you consider the axle as a disc again, the moment of inertia about that axis of rotation through the center is again given by, so let it be I2 now. Okay, I2 is equal to mr square by 2, because you know that small r is the radius of axle. So mr square by 2 is the radius of only the axle. Okay, once you know the moment of inertia of the whole disc, only disc, and moment of inertia of the axle, then what is the moment of inertia of the entire device? That entire device you call it as flywheel. Okay, so moment of inertia of the flywheel as a whole about the axis of rotation is given by, now we have to add these two equations, right? So I is equal to m into r square plus r square by 2 of the wheel, it is, plus mr square by 2, that is for the axle. So put together, just adding with these two, you will get the total moment of inertia of the flywheel. Okay, so this is the expression, the theoretical expression to find or to know the moment of inertia of the flywheel about the axis of rotation passing through center of the flywheel. Okay. Now the question is, what is the formula to find the moment of inertia of the flywheel? Suppose if you are doing some experiment with the flywheel, how to find the moment of inertia? What is the formula for that? Okay. Now let us discuss that part. Okay. So now look at the title. So experimental determination of moment of inertia of the flywheel. Okay. So consider the same flywheel here in the experiment. So how you are using the flywheel in the experiment? So as I told, okay, you have to fix the thread at the peg and you have to wound that thread some number of turns, let us say number of turns on the axle, and other end is fixed to the some known mass. Let us say consider that total mass of the hanging weight is equal to capital M, right? Then its mass will be equal to now capital M into G. Its total weight is equal to M into G. So now to find the moment of inertia of the flywheel, you have to consider what is the total physics behind it. There is a lot of physics behind the simple flywheel. Okay, you have to consider all those concepts here to find the experimental formula to find the moment of inertia of the device flywheel. Okay, so let us consider some experimental part here. So mass of the suspended from the string, how much it is? Let us say capital M, and then radius of the axle. Okay, that is what you have to measure. Let it be small r, and then moment of inertia of the flywheel. Mi means moment of inertia of the flywheel. So we will take it as capital I, and then angular velocity. So because the concept of angular velocity to consider, when the wheel is rotating, what is the angular velocity of the wheel when the mass is just detached? Okay, the moment you release the mass, it starts rotating, you know. So you have to consider the angular velocity of the flywheel. Okay, wheel, that is equal to omega, right? So velocity of the mass when it is just detached. See here, the mass is moving downwards. Okay, it is not a rotational motion, it is a linear motion. What is the mass of that hanging weight W, M, when it is just released? So its velocity you have to consider it as small b. Okay, linear velocity. So rotational velocity of the flywheel is omega, and the velocity of the mass is equal to v. Is it clear? Now look at here, potential energy. So when the wheel starts rotating, okay, before rotating, what is the energy? When it is at rest, you have to consider it is having the potential energy, right? So you can have the equation for potential energy lost by the mass in falling through a vertical height. Okay, so as I told, so it may be falling downwards. Okay, so through that height, how much from this rest position it is falling downwards? You are measuring the height, you know, up to the ground. So depending upon the height of the mass till it touching the ground, okay, you have to consider the potential energy is the product of that mass, acceleration to gravity, and this h. mgh is a standard formula for potential energy. Okay, so mgh you have to consider. Now when it is falling downwards, kinetic energy, it is converting some partial law energy is converted to kinetic energy. What is the equation for kinetic energy? Kinetic energy gained by the mass m. It starts moving downwards with kinetic energy equal to how much? Half m v square. M is the mass, okay, and v is the linear velocity of m v square. But the wheel is rotating here due to that downward motion of the mass. The wheel starts rotating. Okay, so what is the rotational kinetic energy gained by the flywheel then? That is in terms of moment of inertia, right? So that is half I omega square. So there is a equation for rotational kinetic energy in terms of moment of inertia, that is half I omega square, where omega is the angular velocity of the flywheel. Clear? Next, average work done. So there is some work done to rotate the body. What is that average work done? So average work done against the friction per rotation is equal to W, because of course it is made less friction, but still against the friction only it has to rotate from the rest, isn't it? So that is why you are applying the load here. It has to overcome the friction and then starts rotating. Then what is the work done against the friction? That is what actually you are considering W here. Next, energy lost due to the friction, in n number of rotations. For one rotation you are considering the work done is equal to W, and it is assumed that rotating depending upon number of turns n on the thread, it is rotating n number of turns also, right? So if it is rotating n number of times, what is the total energy lost due to the friction? Okay, so that is equal to n into W, right? Total energy lost during the rotation against the friction. Now, so all these concepts are very important. Physics concepts are important, okay, when the wheel made to rotate, because there is a transfer of energy, conversion of energy from potential, rest position means potential energy to various energies here. So what are that various energies? It converts to kinetic energy, okay, part of the energy, and it is also converted for partially for rotational of the wheel, and partially energy lost in the form of what you said, energy lost, okay, the form of some energy lost here in the form of work done, okay. So then according to the principle of conservation of energy in the experiment, okay, you have to consider the principle of conservation of energy. The total energy, whatever the total energy of the flywheel we consider it as potential energy, that is mgh, is divided into number of energies. What is that? Kinetic energy, rotation energy, and total work done last year during the against the friction. It may be heat or etc. Okay. So half mv square is the kinetic energy plus half I omega square is the angular rotational kinetic energy plus nw, that is total work done against the friction, nw. Okay. So note down this basic equation of conversion of potential energy into different forms of the energies when the wheel starts rotating. Okay. So let it be equation 1, and then I will proceed. Okay, now let us see how to find the average angular velocity of the flywheel. Okay, because we have declared that the angular velocity of the flywheel is equal to omega, but at what instant it is? At the instant when the mass is detached. Okay, the attached mass is detached, then it starts rotating. Okay, at that time its angular velocity is omega. So at the instant the mass is detached, the angular velocity of the flywheel is omega, and after some time, that means after t seconds, it comes to rest. Okay, when it stops rotating, it is mass is reaching the ground. Okay, or you can say even after some time the wheel has to come to rest. Then what is its angular velocity? When it comes to rest, its angular velocity is 0, right? Angular velocity becomes 0 after some time t. Okay, now average angular velocity you have to calculate. The angular velocity of the flywheel is now in time t, in the total time t. So that initial angular velocity omega plus 0 divided by 2, so it should be equal to omega by 2 only, right? So average angular velocity is equal to now omega by 2. Clear? Now let us consider. So we have average angular velocity of the flywheel. It is also given by the formula total angle described, because it is rotating, you know. So for one complete rotation, or how many rotation it is making, one complete rotation angle is 2 pi, isn't it? 360 degree. So 2 pi into n, right? N number of times it is rotating here. So 2 pi n by t, you have to divide by t here. That gives actually the average angular velocity. So average angular velocity is equal to omega by 2, and that must be equal to 2 pi n by t also, right? So by rearranging the equation, now angular velocity omega is equal to 2 into 2, 4 pi n by t, 4 pi n by t. So let it be equation 2 for angular velocity of the flywheel, right? Now you know that also the kinetic energy of the flywheel is dissipated in time t is doing work against the friction. Okay, whatever the work done, again work done against the friction is because of the kinetic energy of the flywheel which is dissipated. Okay, so you can compare that total work done dissipated against the friction W. Okay, that is equal to I omega square by 2n now. How it is obtained? So because you can equate just kinetic energy equation as of I omega square in terms of moment of inertia. So it is equal to total work done, N into W. Okay. So by just cross multiplication you can get the total work done is equal to now I omega square by 2N. Let it be equation 3. Is it clear? So now we have the equation for angular velocity and we have the equation for total work done against the friction. Okay. Substitute these two equations now in equation 1. What we have, that is for the total potential energy convert into different forms of the energies, right? That is equation 1. So substitute equation 2 and 3 in equation 1, and then we can do some mathematical simplification to calculate the moment of inertia of the flywheel. Okay. So note down up to this equation 3, then I will proceed. Now look at the continuation of the simplification part. So here from equation 1 we have mgh, potential energy mgh is equal to half m v square actually. So in place of v square I substituted as r square into omega square, because you know the relation between the linear velocity and angular velocity, that is v equal to r omega. Okay, I can take it as now r square omega square plus half I omega square plus half n by capital N into I omega square is there, right? So here all are now in terms of omega square, so that I can take it as now common half omega square in the y equation. So what is the common factor? Half omega square. So left with mr square plus, okay, so only half I omega square was there here, right? So what is left here? Actually only I. So again here also we have I, right? So you can just take that internally common again. So left with only 1 here plus capital N by small n, because half omega square is already taken as the total common here in the square bracket. So inside left with only 1 plus n by n into I as the common between these two terms. Between these two terms I is the common, that's it. Okay. Now look at the next step. So I have 1 plus n by n into I in the left hand side. That means only this term I will take in the left hand side. So remaining all terms I will write in the right hand side. So it is multiplying mgh by 2, okay, 2 mgh by omega square, and only one term is left here. So that is actually minus m. When you take another side it will become minus mr square, that's it. Okay. So just rearranging the equation for 1 plus n by n into I. Okay. Now LCM is small n, so n plus capital N by n and is equal to, so here again capital M is common, so m into 2 gh by omega square minus r square in the bracket. Clear? And then so what I want here, okay, so moment of inertia, where it is, I missed here. So I is equal to, so I is equal to by cross multiplication, so nm divided by n plus n, and it is into 2 gh by omega square minus r square. So this is the rearranging the equation for only moment of inertia of the flywheel. That is what I want here. So let it be equation 4. Okay. And further if I substitute the equation for omega in terms of number of rotations experimentally, what you are finding with respect to time t, you know, so that is actually given by, as per the earlier equation, omega is defined as 8 pi n by t, you know, substitute that omega is equal to 8 square pi square n square by t square comes in the numerator. So 2 was here, okay, so you can cancel 2 and 8 square, left with only 8. Okay. So I is equal to now n m divided by n plus n into gh t square divided by 8 pi square n square minus r square is the another equation for moment of inertia. Okay. So because directly you cannot substitute the angular velocity in the equation, so if we convert it to experimental physical terms, then it is easy for you to find the moment of inertia using the equation 5. Okay. So finally by knowing all the quantities in the right hand side, so we can determine the moment of inertia of the flywheel. Okay. So the terms like n, number of rotations, okay, number of rotations made on the flywheel, capital is number of threads, okay, wound on the axle, mass, total mass attached for the flywheel to made it rotate, and g 9.8, h through which the mass is moving up to the ground, okay, time taken for the rotation of the wheel, etc. So r is the radius of the axle, etc. You can just substitute all the experimental measured values, and finally you can determine the moment of inertia of the flywheel using this formula easily. Okay. So that is all about the determination of moment of inertia experimentally. Is it clear? Okay, thank you for watching.